Hi guys, so we've seen partial fractions. We know what case 1 and case 2 for partial fractions looks like. Now we're going to do a question that actually requires us to do a substitution first. So sometimes doing a substitution could result in the necessity for partial fractions. Let's see how that works out here. There are really two main different types of substitution, or I kind of like look like substitution, two different ways substitution can look that could result in partial fractions, and this is one of them. What I notice about this problem is that there are really just e to the x's everywhere. So it doesn't look very familiar because there are just e to the x's all over the place. So to turn this into a more familiar looking problem, we might start off by letting u equal to e to the x, and therefore du is equal to e to the x dx. Now remember, to help us out with this, we want to remember that e to the 2x is the same thing as e to the x squared, or in other words, e to the x times e to the x. So I'm actually going to just do an extra step here, not necessary step, but that allows me to easily see that my du is there. Because inside of that e to the 2x, it's just e to the x times e to the x. So that right there is my du. Now, every time I see an e to the x, I'm going to be replacing that with u, so that I end up with u over u plus 2 times u plus 1 squared du. Now, in this case, what I can see is that I have a rational function. The degree of the top is equal to 1, and the degree of the bottom here, it might not be as clear, but I have a u plus 2, and then I have a u plus 1 squared, so my highest power is going to be that 1 plus 2. My highest power in the bottom is 3. So I have this rational function. Substitution is not going to work. The derivative of the bottom does not equal to the top. So I start off by thinking about division, and we can say that no division is necessary here. Which brings us to our second step of partial fractions, which is to factor the denominator. But in this case, when I did that substitution, my denominator is already really nicely factored for me. So denominator already factored. Which brings me to my third step, which is to create my partial fractions decomposition. Now I see that u plus 2 occurs one time, but u plus 1 is there twice. It's being squared. So what that tells me is that this is an example of a case 2 problem because one of those factors occurs multiple times. So I have u over u plus 2 times u plus 1 squared is equal to a over u plus 2, and I'm just going to go in order here, plus b over u plus 1, plus c over u plus 1 squared. That u plus 1 occurs 2 times, so it gets 2 fractions to itself each time my power is increasing. That is my partial fractions decomposition. And then for step 4, I'm going to solve for my numerators by multiplying both sides by the original denominator, which is just u plus 2 times u plus 1 squared. And so each of these terms gets multiplied by u plus 2 times u plus 1 squared, which means I have a u left on the left side. And my a, the u plus 2's cancel out, and I just have u plus 1 squared left over. My b, the one of the u plus 1's cancels out, so I have u plus 2 times u plus 1. And then for my c, both of the u plus 1's cancel out, and I just have a u plus 2 left over. Okay, so that's my A here, that's my step A. And then for step B, we want to plug in starting with the zeros of the denominator. So here I'm plugging in u values, not x values. So I'm just going to start off by setting that denominator equal to 0, u plus 2, u plus 1 squared equals to 0. So I get my zeros are -2 and -1. So we'll start with u is equal to -2. U 2 is equal to negative 2. And this gives me negative 2 is equal to a. Negative 2 plus 1 is negative 1 squared plus b times 0 plus c times 0. And so I get negative 2 is equal to a. And that's it. That's my answer. Then I'm going to plug in u is equal to negative 1. And I'll get that negative 1 is equal to a times 0 plus b times 0. And I'm running out of space here. Let me try writing that over. So we have plus c times 0. Then we have u is equal to negative 1. Negative 1 is equal to a times 0 plus b times 0 plus c. Negative 1 plus 2 is 1. And this gives me that c is equal to 1. And that is my c value. I'm done with my zeros. Remember, with case 2, I then pick a u value of my choice, like maybe u is equal to 0 because that's a super easy number to plug in. I replace a and c. And then I solve for the remaining constant. So u is equal to 0. And I will get 0 is equal to a was negative 2 times 0 plus 1 squared, so that's 1 squared, plus b is what I'm looking for. 0 plus 2 is 2. 0 plus 1 is 1. Plus c was 1. 0 plus 2 is 2. So 0 is equal to negative 2 plus 2b plus 2. 2b is equal to 0, and b is equal to 0. Now this thing that happened here, having one of our numerators be 0, can only happen in case 2. Only. And only in the specific case where it happened right here, when that denominator, that u plus 1, was not the whole power. So what showed up in my original denominator was u plus 1 squared. So the u plus 1 squared itself can't, the numerator associated with that cannot be 0. The u plus 2 is only there once. Its numerator cannot be 0. The only place that it could possibly be 0 is that b right there, when the power isn't as high as it possibly could be. So the numerator can only be 0 in case 2 when the power isn't as high as it could be. And I'm just going to really briefly explain why that's the case. I need for the common denominator to be u plus 2 times u plus 1 squared. Let's say that a was 0. So I have 0 over u plus 2 plus some non-zero number over u plus 1 plus some non-zero number over u plus 1 squared. Well, what happens is that goes away and my common denominator is just u plus 1 squared. It's not what I need it to be. But let's say that c is 0. So I have some non-zero constant over u plus 2 and u plus 1. And then I have 0 over u plus 1 squared. Well, in this case, that's just gone. It's like it's not there. And my common denominator would be u plus 2 times u plus 1. However, when it's the b value that's 0, even though that term doesn't show up, my common denominator is still u plus 2 times u plus 1 squared. So this gives the wrong common denominator. Whereas this works out. And so this is the case that happened right here. Our b ended up being 0, and that was okay because it was just that u plus 1. All right, hopefully that makes some sense. Now we have our numerators, and our step 5 is to rewrite the integral. And this gives me, oops, step 5 the integral of a, which is -2. My a was over u plus 2. Plus b, that's 0, so that b term just disappears. And then my c here is equal to 1, and c is over u plus 1 squared. Plus 1 over u plus 1 squared du. Good. Now this first one is just a known form, so this gives me -2 ln of u plus 2. And this second one, remember, we've said we can think of this as u plus 1 to the -2. In the case where the power on the denominator is not just 1, we've got to be really careful. It does not give us a natural log. So this becomes -2 ln of u plus 2. We're just applying a power rule, minus u plus 1 to the -1 plus c. Now I don't have to worry about substitution. The derivative of the inside is just 1, so we can just divide by that constant, but because it's 1, it changes nothing. So my u here, one last step, my u is equal to e to the x. So we want to replace u with e to the x, and this gives us -2 natural log of e to the x plus 2 minus 1 over e to the x plus 1 plus a constant. That is my final answer. And if you wanted to leave that as just e to the x plus 1 to the -1, that's also totally fine. All right, so we started with a substitution that turned into a partial fractions. We picked the substitution because there were just e to the x's everywhere. When something appears a whole bunch, sometimes letting that whole thing equal to u makes the problem look a little more reasonable, a little more familiar. All right, that's all for this video. Bye.